Hello. In this notebook, we are going to learn about graph neural networks from zero to hero. Part 1 consists of fundamentals, understanding graphs and message passing. Most of deep learning assumes your data lives in a grid, pixels in an image, words in a sequence, but a huge amount of real world data is relational. Social network, molecules, citation graphs, road maps, knowledge bases. Graph neural networks are designed specifically for this structure. This is a part 1 to 3. We'll build everything from scratch, starting with what a graph is and ending with a working graph convolutional network trained on a real social network dataset. Block 1 is the normal imports and setup. We use NumPy for matrix math, matplotlib for visualization, and NetworkX for creating and manipulating graph objects. Notice there is no PyTorch yet. We built the first GCN entirely in NumPy to understand the math before we add the framework. Chapter 1. What are graphs? Graphs are everywhere. Graph is a mathematical structure that models relationship between objects. This cell visualizes four common types. An undirected graph, like a friendship network, has edges without direction. A directed graph, like a Twitter follower graph, has arrows. A weighted graph assigns values to edges, like road distances. And a bipartite graph has two types of nodes. Here, users and items, connected across but not within groups. Every GNN paper you'll read works with one of these four types. Next, we have graph representations. Adjacency matrix visualization. Here we have created a 4-node graph. Compute its adjacency matrix using network X and visualizes both the graph and the matrix. The adjacency matrix is the most natural representation. Entry A, I, J is 1. If there is an edge from node I to node J, 0 otherwise. For undirected graphs, it is always symmetric. If I connects to J, then J connects to I. The downside for a graph with 1 million nodes, the matrix has 1 trillion entries, almost all zeros. That is why we need sparser representation for real world graphs. Next, we will compare representations. 4 ways to represent the same graph. The edge list is the simplest, just a list of tuples. The adjacency list maps each node to its neighbors, faster neighbor lookup. The COO format uses two parallel arrays for source and target node. This is exactly how PyTorch and geometric stores graph. Because sparse tensor operations on GPUs work best with this layout. For sparse real-world graphs with millions of nodes but few edges per node, COO is dramatically more memory efficient than any adjacent matrix. Next, you can see the memory comparison between adjacency matrix, edge list, and COO format. Next, we have graph class with node features. In GNNs, node often have feature vectors. Real GNN inputs include two things: the graph structure, who connects to whom, and node features, numerical attributes for each node. In a social network, node features might be user age, interest, and activity level. In a molecular graph, they would be atom type, charge, and hybridization state. Our graph class stores both and provides utility methods like get neighbors and degree. Why do we need GNNs? Here's the core challenge. If you naively flatten an adjacency matrix into a vector and feed it to a standard neural network, a problem emerges. The same graph with different nodes ordering produces completely different vectors. The network treats them as different inputs. Even though they are structurally identical, a good graph model must be permutation invariant. Swapping node labels should never change the output. This is exactly what GNNs are designed to guarantee. Next, we have message passing. Message passing is the universal framework underlying almost every GNN, and each layer first aggregate collect information from neighboring nodes. Second, combine that neighborhood information with your own features using a learnable function. After one layer, each node knows about its immediate neighbors. After two layers, it knows about neighbors of neighbor. After L layers, it has absorbed information from all nodes within L hops. Receptive field growth. This is the receptive field growing with depth on the Karate Club social network. At layer 0, node 0 only knows itself. At layer 1, it absorbs its immediate neighbors, shown in orange. At layer 2, it reaches the neighbors of neighbor. By layer 3, it has information from most of the graph. Three layers of message passing gives a node a nearly global view of the network. You can see here, 0 node, it knows only itself. At layer 1, start connecting with its immediate neighbors. At layer 2, it starts connecting with neighbor to neighbor. At layer 3, it has information from most of the graph. A simple message parsing implementation. Before adding learnable weights, let's see what pure aggregation does. After one round of mean aggregation, node zero's features move toward its neighbor's features. After three rounds, all features are converging toward the graph average. This is oversmoothing, a real problem in deep GNNs where nodes become indistinguishable. Learning when to preserve versus share information is exactly what the GCN's weight metrics do. GCN, Graph Convolutional Network from scratch. The GCN normalization has two steps. First, add self loops, so each node aggregates its own features along with its neighbor. Second, apply symmetric normalization, divide each edge weight by the square root of both nodes' degrees. This prevents high degree nodes from swamping low degree neighbors. Node 2 has degree 3, so its contribution to its neighbors is divided by square root of 3. GCN layer implementation using NumPy. In this code, we have GCN layer formula in full. Multiply the normalized adjacency matrix by the node features. Then multiply by a learnable weight matrix, add bias, and apply ReLU. Next, we have full GCN network. We train NumPy GCN on a small graph with three communities, 9 nodes, 3 nodes per group, and only use 6 nodes for training. By epoch 150, both train and test accuracy hits 100%. The GCN correctly classified all three held out nodes, each from a different community, without seeing them during training. The graph structure does the heavy lifting. The network learned that nodes connected to the same community share features. Next is training the GCN in PyTorch. Now we build the same model in PyTorch, which gives us automatic differentiation, no manual backward pass needed. This particular Colab environment run without a GPU for this notebook, but the code was identically on CUDA as well. Training the PyTorch GCN. The PyTorch version is cleaner. We define weight as an nn dot parameter, so PyTorch tracks it for autograde. The forward pass is 2 lines. project features, then aggregate with the normalized agency matrix using Glorot initialization, also called Xavier uniform, ensures the initial variance is appropriate for the layer depth, preventing vanishing or exploding gradients from the start. Next, we have training the PyTorch GCN. Moving forward, we'll go to Karate Club demo. The Karate Club is a famous dataset from 1977. Wayne Jashri documented a social network of 34 Karate Club members before the club splits into two factors, Mr. High's group and the officers group. We give the GCN only 6 labeled nodes, 3 from each faction, and ask it to predict the remaining 28. The GCN achieves 100% accuracy. It does not just memorize, it learns that who you are connected to predicts what faction you belong to. This was all about this notebook. The key takeaway and summary is graphs have nodes with features and edges representing relationships. They appear everywhere: social networks, molecules, papers, roads. We looked at 4 ways to represent graphs: matrix, edge list, agency list, CO format, each with different trade-offs. Message passing is the core of every GNN. Aggregate neighbor information, update your representation, repeat. GCN adds learnable weight metrics and normalized aggregation to make this trainable end-to-end. And on the Karate Club, a 2-layer GCN trained on just 17% of node classified, 100% of the rest correctly, purely from graph structure. In part 2, we cover graph sage, graph attention network, and phytogeometry. This was all about this video. This was all about this notebook. Thank you for being there in the video.